All right, this is for example 4 from section 1.2, chapter 0. So let's go ahead and look at the problem together, and we'll kind of at the end summarize ways that we can estimate finding the derivative. So we have this mass here. It looks like it's balancing up and down on a spring hanging from the ceiling. Its distance y here is measured in feet from the ceiling, and it's measured by calculate our distance probe each 1/10 of a second, given this table of values in which t is time in seconds. So as you look at this, you can see that the distance from the ceiling is going to be kind of like oscillating. It's going back and forth as it bounces up and down. Okay, so we're going to find how fast is y changing at each of these times. So we're trying to find that instantaneous rate of change, or what we also call our derivative in calculus. So this is going to be the third method of how we can find an estimate of a derivative. Remember, the first one was we just did a ruler on a graph. We found, our slope, rise over run. The second one was we had that table of values, and we used the average slopes of the closest two values. In this case here, we're going to actually approach from the left and approach from the right and use those average rates of change. So we want to find at t equals 3. So what we're going to go ahead and do, and I created this table for you so that you'd stay a little bit more organized as we work through it, is let's go down to the table together. Okay, so at t equals 3 seconds, what we're going to do is we are going to find the average rate of change from 2/10 to 3/10, and also 3/10 to 4/10. So let's go ahead and find the difference between these two y values. So we're going to find the change in y, which is going to be 1.85. And then we're going to go ahead and also find what that rate would be. So it would be 1.85, and it's going to be divided by change in t is just 0.1. Okay. So that equals 18.5. And we're going to also approach from the other side. So we're going to find the change in y here. So the difference ends up being 1.53. We're going to find our rate, so 1.53 divided by, you can see the change in t is always going to be 0.1. So it ends up being 15.3. And then we're going to find the average of these two, which is 16.9. So, and since it's positive, that means that y is going to be increasing 16.9. Again, let's think about what our units would be. Y is measured in feet, so it's change in y, so that's feet on the top. T is measured in seconds, so means it's increasing 16.9 feet per second at t equals 3/10 of a second. All right, so let's go ahead and go down to 0.6 and do the same sort of method. I'm going to use a different color so it's easier to see what's going on. So 0.6, we need to approach from both sides. So the difference here is going to be negative 0.52, and the rate is going to be change in y over the change in t. So it ends up being negative 5.2. We'll approach from the other side. So the change here is negative 1.47. So negative 1.47 divided by 0.1 ends up giving us negative 14.7. The average of these two is negative 9.95. So I'm going to go back up here, and since it's negative, I'm going to say that it is decreasing 9.95, and we know the units feet per second. All right, let's look at the last one they're asking us. So at 1, let's go down to 1, and I'm going to approach from both the left and the right. So this is, the difference is 0.63. So negative 0.63 divided by 0.1 is going to be negative 6.3. Okay, the difference here is going to be 0.52. So we're going to say the rate is 52 hundredths divided by 1/10, which equals 5 2/10. And if we find the average rate between these, it's going to be negative 0.55. So again, I'm going to go back up here, and I'm going to say that it is decreasing So we got that negative rate, 0.55 or 55 hundredths feet per second. All right, part B says that t equals 0.3 is the mass going up or down. Justify your answer. So let's go back to 0.3, and you're going to see that this here is, as it's increasing, is a positive number. So basically that means that as y is increasing, so that means, you know, as we're getting further away from the ceiling, the mass is actually going downward. So let's write that in words together for part B. So I'm going to say at t equals 0.3, the rate is 16.9 feet per second. This is a positive number, okay? This means that the mass is going downward. Okay. All right, so let's just quickly summarize the three different ways we can find the estimate for a derivative. Just put it at the very bottom here. So I'm going to write down that we have three different ways to find the estimates of a derivative. Remember again that derivative is our instantaneous rate of change. Okay, so the first way that we looked at in example 2 was just using a ruler on a graph. So that was just rise over run. Okay, the second way that we worked on that was example 3, was given a table use the average slopes of the closest values and we approach from the left and right. Use the average rates of change.